Good morning, everybody. I'm Pat Griffis, and as it says, Vice President of Technology at Dolby. I'm also past President of the Society of Motion Picture and Television Engineers. Raise your hand if you know what that is. You better raise your hand, Alan. Okay. It's a group that creates a lot of the standards for Hollywood content, and in fact, create a lot of the standards that I'll talk about today for HDR. So we've talked a lot about video coding this morning. One of my jokes about video coding, those who know me know I like to make quips. One of the quips is compression has never been shown to improve picture quality. It's all about bit rate efficiency, right? And as you heard today, in fact, Jan brought up a good point. When we talk about power consumption, I think 70% of the internet traffic at prime time now is all for media, like Netflix and others. So clearly, bits are bucks, one of my other quips, and of course, as Jan pointed out, bits also are power. So if we can have greater efficiency with bit rate, we can save power and keep the planet greener for a little bit longer. So today I'm going to talk a little bit about HDR and some of the history and how we got there. You've heard a lot of terms like PQ for perceptual quantizer. For those in the audience who aren't techies, it's probably all alphabet soup for you. So I'll try to bring some perspective from a normal humanoid viewpoint. So we'll talk a little about the history of HDR. And one of the exciting things about VVC is it was designed from the get-go to do HDR. And hopefully after this presentation, you'll see that HDR has gone from a dream to mainstream, and VVC is the perfect vehicle to help carry it even further. So, if you were starting with a clean sheet of paper as an engineer and said, I want to design for the perfect technical solution to match humans, well, that dream would be opening your windows and looking out onto the Olympics and being able to see it as if you were looking through a window. Technology has not quite gotten us there. But if you start with that dream, what are the parameters that we have that could help us get there? Well, first of all, higher spatial resolution, which means more pixels. We'll talk a little bit about that. Second parameter is more frames per unit time, or what I like to call faster pixels. And then my favorite topic, and the one we'll spend a lot of time on, how about if every one of those pixels, no matter how many or how fast I'm sending them, have higher dynamic range? What does that mean? Brighter whites, blacker blacks, more color, more saturated color. All of those contribute to making each pixel better. So let's talk a little bit about more pixels and faster pixels. So here's a summary for 4K, and you often hear 4K used. Actually, 4K isn't really 4K. It's 3840 pixels per line, but it's a lot easier to say 4K, so we just round it up. And then doubling the number of lines from traditional HD, by the way, which is 1920, so 1920 horizontal pixels for HD. You double that double the number of pixels per line, double the number of lines, so it's 4 times more, or about 8 million pixels per single frame. But now, I want to send those frames in unit time. So 24 frames per second, which is the standard rate for Hollywood movies, of course, is one of the options. And then if you're doing sports, you might want a lot more frames per unit time. So imagine 8 million pixels, by the way, each which have so many bits. Oh, and by the way, they also have 3 colors, 120 of those per second. That becomes a lot of data. But it gets even worse with 8K, because effectively you now have 4 times more pixels per unit time. So as we make better and better quality images, it's taking more and more pixels. And remember, bits are bucks, or euros, I guess, in Europe, or won in China, or yen in Japan. So now comes HDR. High dynamic range, we get closer, and I often joke, every time you open your eyes, you see high dynamic range as a human being. The problem has been we haven't been able to reproduce it with our technology until recently. So let's talk a little bit about what that means from the viewpoint. Again, remember a clean sheet of paper. What would we design for? Well, the human eye. So understanding how we as human beings see light in much the same way as we've now understood how human beings hear sound would be useful. So first, some light nomenclature, a little pun there. When we talk about how we see light, the key term is called luminance, and the measure is in candelas per meter squared, which colloquially, a lot of us in SMPTE came up with the term. It's kind of hard to say candelas per meter squared every time you have to use the term. So we created a colloquialism called nits, and I'm nuts for nits, just so you know. And it came actually from the Latin natere, which means to shine. So when you hear the term nits, know that scientifically we're actually talking about candelas per meter squared. And what does that mean? Well, this is a similar representation of how we as human beings see light and our spectral response. And as many as you may know, we're most sensitive to green. You might guess that probably going back a million years, if you saw something green, it usually meant you could eat it. So being sensitive to green was a good survival capability. Red and blue are also there. But basically, what a nit is this measurement. And so as I increase the brightness of something within the visual spectrum, as it gets brighter and brighter, or a step in contrast sensitivity, it's something we measure and we can see as human beings. And by the way, you'll hear the term contrast sensitivity said a lot. How many know what that means? No one? Not even Alan? I know Jan knows. So if I put two white squares on a TV screen and I gradually increase the brightness of one until you go, I see a difference, that's a step in contrast sensitivity. And this is very important because our eyes, in addition to being nonlinear, aren't uniform in how we see contrast. And I often tell my friends who say, f-stop, which is double the amount of light. So many f-stop. My LG friends used to say this all the time about OLED TVs. Well, not all f-stops are created equal. Our contrast sensitivity at higher absolute brightness is much greater, and we'll talk about that in a moment. So it's important to understand that if you're designing a system, especially if you have to compress it. So let's talk a little bit about the real world. In the real world, now that you know what a nit is, we deal with tremendous amount of dynamic range. In fact, 10 orders of magnitude from a noonday sun. If you look up at it, it's 1.6 billion with a B nits, which is why even when you're squinting, it hurts because it's extremely bright. And of course, as human beings, we used to hang around in caves. They're not very bright, almost near zero light. So with those dynamic ranges, human being visual system actually visually adapts. We have the iris, and it opens and closes based on the ambient environment we're in. So if we're outdoors, our iris shuts down. If we're inside in a cave, our iris opens up. So the question is, for entertainment purposes, what would be a useful range? Well, we'll get to that in a moment, but starting with technology today, the typical television system, which in the old days, production, distribution, and playback on TV sets were all the same. Life was so much simpler in the analog world. And TVs were designed for that. And then white was about 100 nits for a television set. Compare that to 1 billion nits for the sun. And over the years, as televisions got better and better, they far exceeded the standard. In fact, most TVs today are brighter than that reference standard. And just for comparison, in cinema, we all love movies, but we watch them in a dark environment. The cinema standard was actually half of television for many years. So the question is, again, back to that clean sheet of paper, what would we design our system for human beings to try to do something that's scalable? Well, let's take a look at the real world. Here's some examples from our Dolby Lab. Remember, 100 nits was the absolute brightness of traditional TVs. The one I always like, you see where it says 2100 nits? That's blacktop. Wait a minute, blacktop. It's supposed to be black, yet it's 20 times brighter than a typical TV set. And notice the reflection over here. Let's see, I don't have my mouse, but this one. That's a specular off a car, and that's not a typo. 330,000 nits, or 3,000 times brighter. So how the heck do you deal with that? And here's another example. A flower in the sun, in that yellow, is 14,000 nits, or 140 times brighter than the brightest white of traditional television. And this is in the real world. So color can also be extremely bright. And typically, many of us have watched fire and television. In the old world, you'll notice the fire seems to be white because it's clipping. But if you look at a real fire, there's no white in there. So those are two considerations. The next element is, let me close that, sorry about that. So the next notion, this is something we discussed in SMPTE a lot. The thing you're looking at on the left there is a plot of XY coordinates of the colors that we can see, developed by CIE many years ago. And that REC 709 is an ITU spec for the color primaries of legacy analog cathode ray tubes. And as you'll notice, the triangle is a lot smaller than the locus of all the colors we can see, and this has been a limitation we've lived with. And the one thing that's missed in this is, well, how bright can each of those colors be? And you'll see here what this notion of a term we created in SMPTE called color volume, which is the locus of all the reproducible colors at all their allowable intensities. And not all colors are created equal, because we tend to have a color additive system where white is the sum of red, green, and blue. And you remember that, locus of the colors we can see as human beings. Green is always brighter, and so it is in this diagram. And the white from that two-dimensional plot goes to the three-dimensional color volume. And here's another way of looking at it. And you might say, who cares, Pat? Well, we care, because when we want to try to reproduce an image on a television set, the color volume of that display defines the colors that we can reproduce. And so this notion of color volume, it's one of the things I want you to leave this session on. You're all going to walk away being color volume experts. It's not color space anymore, it's color volume. It's the palette of all reproducible colors at all allowable intensities of a display. So what does that mean from a practical viewpoint? Well, take a look at a picture image on the right, our dream of the Olympics, and now take every one of those pixels and reproduce it within the color volume of that display, and you get an image like you see on the left. I often think of it as a cloud of mosquitoes flying around, and I'll show you an image in a moment. So this notion of a color volume of a display and the pixels that are coming to it create a capability. And in fact, with HDR, higher dynamic range, we have a larger color volume. So now I can reproduce more of the pixels that might have been in the original scene. Hopefully that makes sense. So HDR gives us a greater color volume or a bigger palette to reproduce our colors. So this is my favorite example. I watch this time and time again. On the left, you're seeing a color volume of the display, and in real time, all the pixels of the image on the right. And the three planes, if you can see them, are showing the brightest pixel, the darkest pixel, and the average level. And try to guess which pixels are which as you're looking at that. Obviously, the blacks are down at the bottom, the various colors go shooting off to the side, and of course, the really bright things like that arc welder are near the top. Here you've got some purples and colors. And I found this, even for management who have no idea what bits are but know what bucks are, this is very helpful for them to visualize what we're talking about with high dynamic range and how we can reproduce now with this new palette images that are much more realistic looking. Can I move on? Some people are still watching. All right, I'll leave it. Yeah, so this is a very interesting one too. You look at the colors kind of there in the middle. All right, so one of the interesting points, my dynamic metadata was mentioned earlier, and I'm going to now explain a little bit about the benefits of that. But you see here in a real image, as the pixels move up and down, knowing a lot about the content itself could be very useful in trying to map that content to different types of displays. Okay, let's move on. So here's another example now with a static image, but again to reinforce this notion of color volume. This happens to be a display that had a 4,000 nit color volume, and then you can see in sort of the gray what a standard dynamic range image, that legacy 100 nits, would do. And here in this image, we have pixels actually from the captured image that go way outside the standard dynamic range. And so having a color volume that could support that would allow us to reproduce a better image. Okay, so back to our homework assignment, which is what would we design with a clean sheet of paper for human beings? Well, first question is, how black should we go? Well, it turns out if you're in a cave and you're there long enough, even if there's only a few photons floating around, you can begin to perceive them, but it takes a long time for our eyes to adapt. So the good news is, each f-stop you go down, and f-stop is doubling of light. As you go down in the blacks, our sensitivity is not very good. And it turns out with less sensitivity, we need less bits to represent that. So in developing a standard, the decision was, let's just go all the way to black. It doesn't take a lot of bits to represent that. That was the easy one. But what about white? White always being the sum of red, green, and blue, the brightest colors. As I mentioned today in cinema, the standard is 48 nits. They use this legacy thing called foot Lamberts, which is another way to measure reflective light, but it's become obsolete. Everyone's kind of moved to candelas per meter squared. In terms of what's commercially available, there are actually this is somewhat dated, there are TVs out there now that can do 3,000 nits. So the TV devices have gotten much better. Even computer displays, Apple's got one that does 1,500 nits. The best of class commercial devices today are 4,000 to 5,000 nits. So it turned out we did some tests at Dolby and brought in a lot of the studios and concluded that 10,000 nits, not 1.6 billion, we're not going to have nuclear power plants to drive our TVs, but 10,000 nits was a useful range. And so we actually brought a number of folks in, looked at them, we said for humans, 10,000 is pretty good, especially if you want to see those speculars and make them look somewhat realistic. So the conclusion in the work that we did at SMPTE, and this is really done with a lot of the Hollywood studios, was that 0 to 10,000 nits will satisfy the majority of consumers for entertainment purposes. Now, granted, if you had an outdoor scene that was very bright, you adjust the iris on your camera and you bring it down. But within any given environment, particularly if you have something that's really bright, you'll have a local contrast reduction. If you ever watched a bright scene in a TV set, you put your hand over the bright thing, suddenly the darks start to come up. So there is a limit within any given environment of what's useful. But for purposes of the standards work, we concluded 0 to 10,000 nits was a useful range. You might not use it all, but would be a useful range. And the analogy I often make for non-technical people, everyone seems to understand about audio. What's the frequency range of audio? Anyone? Useful range?
About 40 to 25K.
Okay. Typically 20 hertz to 20 kilohertz, unless you're a dog, and then you can hear 40. So, but most people understand that, and the technology has improved so much that audio is almost trivial, at least in terms of frequency response. We never had a similar number for contrast range for imagery. So 0 to 10,000 nits is sort of that equivalent in frequency response for audio. All right, so now we know what our range is from black to white. What about the curve to get us there? Now, those of us who are old enough to remember cathode ray tubes, like me, It turned out they had a characteristic that as you put current into them, the brightness was very nonlinear. And it turned out that nonlinear function, or so-called electro-optic transfer function, there'll be a quiz, so you better remember that one, EOTF, is simply a way of saying, as I put voltage in, how much light do I get out? And remember, the human visual system, as you put light into our eyes, we sense it as well. Well, that curve, which is based on the electro-optic characteristics of cathode ray tube, better known as gamma, was what was used for many years in the range of typically 0.1 to 100 nits that led to our standards. Well, we're starting from scratch. We're saying, nope, we want to go from 0 to 10,000 nits as our design goal, and to leave headroom for future growth. And believe me, at the time we did these first tests, when we suggested 10,000 nits, people said, how the heck are you going to do that? And now we have displays that can do it. The other thing is, what kind of quantization precision do we want so we don't get artifacts? Everyone's seen mosquito noise or blurring errors or squares. I often joke consumers are experts on compression because they know what television's supposed to look like, and when it doesn't look like TV, there's something wrong. So 10 to 12 bits seems to give us enough precision to avoid quantization based on a lot of work. Now the last thing is, what should that electro-optic transfer function be? Well, it turns out this guy by the name of Robert Barton back in the 70s and 80s did a lot of work on measuring the contrast sensitivity of the human eye to give us a curve that we could use to follow. And that was standardized in SMPTE. SMPTE standards typically have an ST 2084 back in 2014, almost 10 years ago now. And it was affectionately known as the perceptual quantizer because it modeled the human visual system. We didn't make it up. Actually, Dolby did a lot of the work, but someone came up with the name perceptual quantizer. Again, a lot easier to say than ST 2084. So you're now all PQ experts, and you know where the curve comes from. So let's look at that curve. Remember, contrast sensitivity, 2 white blocks, raise the brightness until you see a difference. That's a step in contrast. And gee, guess what? The human eye is very nonlinear in even contrast sensitivity. We're much more sensitive, as this shows, at higher brightnesses than lower brightnesses. And Barton made a plot, and so we call it affectionately the Barton ramp. And it's standardized in some ITOR reports. But it's the consensus threshold of human visibility. And so if something is above that threshold, contouring could become visible. If something's below that threshold, the contouring would not be visible. And of course, since bits are bucks, we want as few bits as possible to represent. Okay, so here's what the result of the PQ curve was for 10 bits and 12 bits. And you can see on the right, and this is in the handouts, you can look at it in more detail. For PQ 10-bit, you might get some perception depending on the kind of content. With live capture with cameras, they tend to have camera noise, which can mask some of the artifacts. 12 bits was shown to be most efficient. And for reference, here's a 10-bit gamma, 15-bit gamma, and then log. And in fact, the visual model for HLG is based on the fact that we're log at one part of our visual system and gamma at lower part, and so kind of find a switching point between the two. And then this 16-bit open EXR, which is a linear representation. It's why you have the sawtooth. You just up the exponent, is very good. So bottom line, in terms of this next generation and our 3 knobs, more pixels, faster pixels, and better pixels, this is some work done by Warner Brothers to say the benefits of the various knobs we turn for visual acuity. And you can see that increasing color volume and dynamic range doesn't take a lot of extra bits. This is before compression, remind you, but offers a lot of benefit and perceived value. So, bottom line is we need more, faster, and better pixels, all requiring more bits. And Jan mentioned XR and AR. You get a lot more bits when you go to volumetric. So there's plenty of future for VVC. And the point I want to make to you is that HDR is now deployed in billions of products. In Dolby's case alone, and we're just one of the companies, Dolby Vision is in 1.5 billion devices. Televisions, mobile devices, even computers and gaming now. And in fact, about 225 million TVs, this is back in 1920, 58% included HDR functionality globally, and 10% even went above 500 candelas per meter squared. That number has increased dramatically already since then, and many support dynamic metadata, which you kind of got a sense of. I didn't have time to cover that in this presentation. And HDR content, of course, is in cinema today. Dolby Vision in Dolby Cinema. You can see movies. Also, there are other formats. Blu-ray, which seems to be fading off into the sunset. Broadcast. One we didn't talk about, in video encoding, typically is one-to-many, kind of stuff that Jan's doing. But we see increasing growth in UGC, which is one-to-one. So there's a question, can VVC actually help those areas as well? So let's move to VVC. I think, as was mentioned, I love the quote, HDR is now a first-class citizen. This is from the text of the recommendation that points some of the things you've heard many times today, that VVC was designed from the get-go to cover HDR. So HDR is now mainstream, bits are bucks, we want to have more HDR and more devices. VVC is designed, and we'll talk a little bit about some of the tools that VVC has for HDR. And one of them you now hopefully understand for you non-techies. If you hear the term mastering display color volume, when the content is created on an HDR display, one of the things that's helpful to know is what was the brightest white in that display? What was the color palette that was available? Those are standardized in SMPTE ST2086 and can be delivered along with the content. So a downstream device, knowing that information, can decide how to render it for the capabilities of its color volume. So MDVC is one of the things that is specified. The transfer characteristics for HDR, now you know what PQ is. Hybrid log gamma is a variation on PQ that tries to take legacy gamma and extend it into HDR. And then SCI messages, we talked a little bit about that already today, so this is kind of summarizing that. But VVC has a lot of tools to support HDR. And particularly the video usability information, the supplemental enhancement information that point to a thing called CICP, or coding independent code points, that allow a service to specify things like, is it a PQ curve, is it hybrid log gamma, some of the color primaries, all these things that are helpful for downstream playback of HDR. This is kind of a conclusion and a rehash of some of the stuff you heard earlier about VVC definitely being in a lot of the standards. So repeat, I think Alan had this table in his presentation. And I want to emphasize in Brazil, which seems to be moving rather rapidly, they're designing their solution from the get-go to support HDR. And again, another rehash of some of the deployment status in terms of encoding, as you've heard from Jan and others, open source tools from Fraunhofer, software decoding, we've had a lot of discussion about that, and then hardware decoding tools are out there as well. The last thing I'll leave you with is the Media Coding Industry Forum. Alan referred to this a little bit earlier. These are some of the companies in it. There are a lot of us that think VVC is going to be the next big thing, and perhaps a little more optimistic in terms of VVC deployment than some of Jan's prognostications, because I think it will be driven by a number of things. The idea to exploit HDR, the growth of virtual reality, although I joke VR is still a virtual business. I think the technology will drive it, and some of the applications are exciting. So, in conclusion, going to need more, better, and faster pixels. HDR is already mainstream now. There's no question about it. And VVC is on its way from becoming a dream to go mainstream. And with that, thanks.